the other kids was a boss.
You should edit out the part where he has to.
I don't think they caught that. They stopped after the 30-minute mark, so I reset the recording.
When did you start right now?
Yeah.
What?
So that was half an hour already?
Yep. That was like a good time to get a drink. Go to the bathroom. People are watching.
Wait, you started back up again?
Yes.
Okay. Alright, so the first couple steps are easy, I guess, because you just plug it in, right? This is e to the x plus h minus e to the x over h. I don't know, what should we do now? Yeah, it's basically the same thing over and over again, right? It was whether it was binomial theorem or there was sine or whatever, I have to do something with the e to the x plus h. What's the only algebraic thing that's really possible? Yeah, just kind of like, yeah, he says take out e to the x. Just rewrite it, just use exponent rules, right? This is just e to the x times e to the h. Just by exponent, right? Yeah. And so you can just factor out, an e to the x, and you get e to the h minus 1 over h. Okay. One more thing you should think of to do at this point.
Oh, spoiler.
Something that came up already last class, a couple times we did something just like this. You're all thinking, we're being shy. Yeah, we can just take the e to the x out because it's just like not part of the limit, right? Take the limit as h goes to 0, so h is a variable which is changing, e to the x is just x, we treat x as a constant. So this really becomes e to the x times the limit as h goes to 0 of e to the h minus 1 over h. Okay. This is already quite deep because this limit, let's suppose for the moment that this limit exists, that it's some number like 5, all right? I have just shown you something very deep and important, which is that the rate of change of this function is some constant times this function. In other words, the rate at which an exponential function increases is somehow proportional to another exponential function. Okay, and in fact, this is something that I do with my functions class when we're talking about rates of growth of polynomials, which we did, I think, last class. Take the function f of x equals 2 to the x. And I can make a quick graph of this, right? I plug in 0, I get 1. I plug in 1, I get 2. I plug in 2, I get 4. 3 is 8, 4 is 16, and let's go up to 32. Okay, so what does this exponential function look like? Points. It looks like this. Okay, and then let's look at the rate of growth. How much does this function increase between 0 and 1? 1. So by 1. Then it goes up by 2. Then
4, 8, 16.
Whoa. Okay, so fundamental principle of pre-calc B, the rate at which an exponential function grows is exponential. Right? Exponential functions grow exponentially. Okay, so that's a thing, all right? So, and now we've sort of shown this with calculus. Okay, there's one flaw in this argument, which, what's really kind of wrong about what I'm now that you actually know calculus? What makes this whole picture kind of bogus a little bit? No, not that it's curved. Okay, well, what do you mean by that?
I don't know, it's like,
What was I actually computing? Are these derivatives, these red numbers?
Found the slope, the general slope.
Yeah, can we use like good vocab? What do you mean the general slope?
Like you're just like average velocity.
Average, yes, average, exactly. 1 represents the average rate of change on the interval from 0 to 1. 2 represents the average change, et cetera, right? So they're actually like secant lines here, right? I'm not actually computing derivatives. If calculus were this easy, we wouldn't need to like do limits and stuff, right? These are, so this is not telling me, although these numbers are very pretty, it's not telling me the instantaneous rate at which this function is increasing. But that's what calculus is about, right? It's about at a particular second, at what speed is the function increasing. This just says that the average rate of change over these intervals is growing exponentially. So, okay, so what is this number? Okay, spoiler alert, it's 1. This is 1, this limit. And so, in fact, the derivative of e to the x is e to the x. All right, now, how do we show that this is true? Well, there's a couple things we can do. First of all, your book completely cheats and just says, oh, this is just the definition of e. It just defines e back in chapter 0 or whatever. Chapter 1, to just be this. Okay, well that's just lame, because that's not the e that I know. The e I know is the one that came from the compound integer version. So, alright, how do we do this? It's kind of a little bit tricky. One thing that we can do that's kind of exciting is to take a closer look at this limit and to see, does this particular limit remind you of anything? Okay, it reminds me of something. It's actually a derivative. If you rewrite this as the limit as h goes to 0 of sort of e to the h minus e to the 0 over x minus 0, then in fact...
Wait, why is it x minus?
H. Then in fact, that limit is just a derivative. And maybe the picture will be better. So here, if this is the e to the x function, and this is 0, then I'm going over a little bit, I'm calling that h, and that point is h comma e to the h, and the secant line, and that point is of course 0 comma 1, so the secant line through those two would be e to the h minus 1 over h minus 0. Does everyone see that now? Okay, so in fact, this limit is, I can interpret it geometrically as the slope of the tangent line to the graph of e to the x at x equals 0. And it doesn't look like it at all on my picture, but what I'm about to prove to you is that this slope is 1. This looks actually terrible on my picture. Okay, anyway, the slope is 1. And what makes the e to the x function so special for calculus is that it is the precise exponential function which has slope, which is a tangent line of slope 1. If you picture all the family of exponential functions, you know there's 2 to the x, there's 3 to the x, there's 4 to the x, there's 5 to the x, they all look roughly similar, right? They all like start slow, they all go through that point 0, 1, the magic point, they all get really big. But they all have different slopes at 0. The e to the x function has a slope 1 at 0. And that's what makes it, okay. So how do we do this limit? How do I show that this limit is 1? Well, you're not going to believe it, but this is what we're going to do. We're going to do the only thing that we can do, which is use the definition of e. Unfortunately, the definition of e is itself a limit. So yes, sir, that's right. We're going to stick this entire thing in here. So we're going to get double limits. This is the limit as h goes to 0 of e, which is the limit as a goes to 0 plus of 1 plus a to the 1 over a. That whole thing is being raised to the h power. Following all this? All right, take that as a yes. Minus 1 all over h. So I have this kind of monstrosity, but in some ways it's the only thing we can do, right? Is just use the definition of e. Okay, now, something kind of, this double limit thing is like some advanced calculus thing. I don't even know how this stuff works, but does anyone have an idea of something we can do that seems semi-legit, but is maybe legit, but is actually fun?
Isn't there something special when you like raise a limit to a power? Can you take the power?
Take out the power.
Take down the power?
Okay, it's even more. right? H is going to 0, but A is also going to 0. So it's like, you know, I have two variables, they're both going to 0.
So you just replace.
So they're really just all the same. Let's just call all the variables the same. Because these two variables are both essentially the same thing. They're both going to 0. So I'm good. That was the wishy-washy step. It's only slightly wishy-washy. Actually, the more you think about it, the more reasonable it seems. So what we're going to do is we're going to just replace all the A's with H's. Because A is just a number which is very, very, very small, and so is H. So this double limit thing reduces to, well, it's 1 plus, instead of A I write H, to the 1 over H. All of that is being raised to the H minus 1 over H. Now some magic happens.
It's just to the 1.
Yeah, so that's like, these two eat each other.
Yeah.
So then it's 1 plus H minus 1.
The ones still each other.
H over H, and it's 1. Ta-da! Okay. Whoa. What we have just proved is that the derivative of e to the x is e to the x. This is actually something like pretty incredible. This says that there's this function, e to the x, which at every single moment, the rate at which it is growing is precisely equal to itself, to its own value. If I want to know how fast this function is increasing at 2, I go to the function, that's 2 comma e squared, which is about 7. At the point x equals 2, the function is growing at a rate of e squared. It's a function which is its own derivative. It's kind of incredible. Arthi, are you impressed? All right, more. Now we get to the useful part of the lecture, homework. Let's go over some homework for 15 or 20 minutes. I thought this homework was pretty hard. I looked back at it. And then I guess we'll call it a day.
Can you do the hard ones first?
Do the hard one first so we don't run out of time? All right, I thought we would do, I made a list of the ones, I wanted to do like 8 or 9 problems actually. So I guess we could pick and choose. Let's go in some kind of semi-order. So I don't know, the ones I thought I would do, the ones I thought were worth doing were possibly 47, 50, 52, 54, 77, 94, 103, and on the other page, either 65 or 63 and 77. I thought we would do all of these, but probably we don't have time to do all those.
Second page first.
Sure, I guess.
Oh, 65, yeah.
I guess we still have a little bit of time. We have like 20 minutes. Should we do 65?
Yeah, that's a good one.
Okay, so those of you viewing at home, you should now take out your homework that you have already completed prior to viewing this lecture, and you should follow along. So 65. This is similar to another kind of problem that I did. This is 65 on page 136. So this is after you already know the power rule. So here we go. This is what this is what the problem says. It says, take a function of the form k over x, and then there's also a line, y equals negative 3/4 x plus 3. And here's what it says. It says, find k such that the line is tangent to the graph of the function. All right. Well, how are we going to do this? Of course, I recommend making a little picture. Now, unfortunately, it's difficult to draw a graph of fx equals k over x. I don't know what k is, and I'm not sure whether k is positive or negative. So let's just guess that k is positive. If I guess that k is positive, then my graph's going to look something like that, right? All right, so let's just hope that's true, and I'll adjust if I have to. Then there's a line. The line is y equals negative 3/4 x plus 3. So let's go over to 3. Y-intercept 3, and negative 3/4 means slope is negative 3/4, so down 3 over 4. So that means the line is like this, right? So I think that means I guessed right. Do you guys agree? I guessed right that k is positive. Okay, and so now I'm starting to think about this because, you know, you gotta do some thinking in math. I'm looking for that line. No, not that line. What am I looking for again?
K.
Oh yeah, looking for the k such that this line is tangent to this curve. Okay, Arthur, you with me? Good. So basically, I know what this line is. And I can maybe think, so this is my original function f. And this is just the line, this is the line negative 3/4 x plus 3. In fact, maybe you want to even give this a name, like a new function. You could call it maybe the g function. The g function is, well, it's negative 3/4 x plus 3. What's the one thing I don't know, basically? I don't know, well, I don't know what k is. I guess there's another two things I don't know. I don't know what k is, and I don't know what that point is, right? That's the whole thing, is figure out what that point is. Okay, so maybe I can figure out what that point is by just giving it a name and doing some algebra. So what is that point? Well, let's just call it A. So I'm just gonna agree to call that point A for the moment. So it is some particular number. Well, what's the y value of that point? It's just f of A. Or I might write it as k over A. Okay, now here's a crucial observation. I also know that this tangent line intersects at that point A comma f of A. So not only can I tell you that that point is A comma k of A, but that point must also be A comma negative 3/4 A plus 3. Right? Because the line goes through that point, so that point must be on the line. Alright, so that gives me one of my two equations relating k and A, right? The first thing I know is that k over A, the y value of the point on the function, the tangent point on the function, has to equal the y value on the line. Okay, but there's a second thing that I know. Of course.
The derivative has to equal the slope.
The derivative has to be equal to the slope. So without further ado, let's take the derivative of this function. Now, I always recommend, prior to differentiating, to write it in a so-called derivative-friendly form. So fx equals k over x, I'm going to rewrite that as kx to the negative 1, because that makes it easier to differentiate. So now we take the derivative and we get, negative k x to the negative 2. Yeah? Okay, so in other words, the derivative of this function is negative k over x squared. And now, that's the derivative in general. The derivative of that particular point, what is f prime of A?
Negative k over a squared.
I just plug it in. It's negative k over a squared. And so my second equation is that the derivative of the function at this point has to equal the slope of that line. And so negative k over a squared has to be negative 3/4. Does this make sense? Did anyone do it? If you did it and got it right, did you do it this way? Ish?
Yeah.
Ish, okay. Alright, now you have a system of equations. In interest of time, I'll leave that, and you still have 3 or 4 minutes of algebra left to do to finish that off. Okay, good, that was 65. More, 77 is a very similar kind of problem. Actually, it's sort of similar to a problem we did last class. Number 77 says, actually the directions were a little bit confusing, but basically, they gave you a function, and I like these questions because they really test if you understand what a derivative is. So they gave you a function, and they also gave you a point, and the point was negative 4, 0. Note that that point is not on that function. And it said, find an equation of the line which is tangent to the graph of the function through the point. Okay, well, you just have to do the same thing every time, which is to make a picture, start drawing, and start thinking about what's going on. So here is my function, f of x equals root x. And I have some point negative 4, 0. So that's over here. And there is a line which is tangent to this function through that point, negative 4, 0. And I need to figure out what I think they wanted the equation of the line, right? Is that right? Okay, how do we do it? What should we do? Camille, what should we do?
Not sure.
Not sure. What should we do? Name the point. Yeah, this is basically the same idea, right? Name that point. Well, it must be A, comma,
F of A.
f of A. In other words, A, comma, root A. And now, what? Actually, this is easier than the previous problem.
Figure out the slope.
Yeah, figure out the slope, right? What is the slope of this line? Well, in fact, the slope of the line can be computed in two different ways, right? The slope of the line is just, well, first, okay, so yeah, so the slope of the line can be computed using these 2 points. It's change in y, in other words, root a minus 0, over change in x, in other words, a minus -4. But also, the slope of that line must equal the derivative of the function at that point. So let's take our function, which is root x. I encourage you to rewrite the function in a derivative-friendly form. It's x to the 1/2. Everyone with me? Okay, then we differentiate. If we differentiate, we get 1/2 x to the -1/2 by the power rule, which, by the way, we're continuing to just trust me that the power rule works for fractional powers, which we'll prove later. Okay, I always like to rewrite it in without negative exponents. So in fact, f prime of x is going to be 1 over 2 root x, right? Okay, so if that's the derivative in general, the derivative at a is 1 over 2 root a. And so, again, that gives me my equation, and then I just solve. Can we skip the solve? Can we skip the solving?
Yeah.
Okay, more. We still have 10 minutes. That clock's 6 minutes fast. Let's do more. Which of these remaining ones would you like to go over? The last 3?
The last one.
The last one? Oh, the last one's quite technical, interesting problem, but I guess we can do that really fast. So the last one says, yeah, let's do that. Number 103, so it gives you this function, which looks like this. Gives you these 2 functions, right? In fact, we've talked about this kind of thing a lot, so it should be a little bit familiar. We looked at this function f, which was x sine 1 over x almost all the time if x is not 0, but 0 when x is 0. What does this function look like? Well, we've graphed it so many times. X sine 1 over x, it has a y equals x envelope, and then it goes crazy in between. And even I know the end behavior now, right? Because this keeps coming up over and over again. What is it? It is 1. End behavior is 1. Okay. So, and this function's even, so it kind of does like a and it's kind of crazy near 0, right? And in fact, it's undefined at 0, but they patch up the undefinedness by defining it to be 0 at 0, right? Is this making sense? Okay, and then there was a different function g, which looks very similar. G is x squared sine 1 over x when x is not 0. But again, it's 0 when x is 0. So what does this look like? Well, this now has a quadratic envelope, but it's still that same kind of crazy function, and we proved that actually this function is odd and kind of goes off to infinity, so it's going to do like something like that. Okay, so again, these functions are both continuous at 0 intuitively, right? And in fact, that was the first thing they asked, right? Show that f is continuous but not differentiable, and show that g is differentiable. Okay, how do you show that f is continuous? So how do we show f is continuous? This was really testing your theoretical understanding of the definition of continuity. What does it mean to be continuous?
So when you have to take from both sides equals f. So
Yes, that the limit of the function equals the value. Okay? So to show this is continuous at x equals 0, I simply take the limit as x goes to 0 of f of x, and I have to show that this is f of 0. Right? Say right. Okay, well what is the limit as x goes to 0? Well, this is like one that we've done before, right? Can I skip the details because we've done this before? Well, I guess I could do it. We do the limit switchy, right? Who knows what I'm talking about? Well, actually, do I have to do limit switchy? No, I guess I could just, where's that? What's going on here? X sine 1 over x. Oh yeah, so why is this 0? It's just a squeeze theorem situation. Sorry, I blanked out for a second. It's just a squeeze theorem. Yeah, it's just a squeeze theorem. Yeah, the x sine, so x sine 1 over x is going to be between, right, since sine, no one there was going to help me out. You were just going to let me say wrong crap. But yeah, sine 1 over x is between negative 1 and 1. So x sine 1 over x has to be between negative x and x. And thus this function, though it behaves crazily near 0, is contained within two other functions which are both going to 0. So without writing all that out, I have just shown by talking it out that the limit as x goes to 0 of x sine 1 over x is just 0, which is f of 0. So that proves that f is continuous. Good so far? Good so far? Okay, now let's show that it's not differentiable at 0. Well, what is f prime of 0? F prime of 0 is, by definition, just the limit, as x goes to 0, of f of x minus f of 0 over x minus 0. So let's see if this limit exists. Wow. This is going to be the limit as x goes to 0 of, well, what is f of x? Well, everywhere but 0, I follow that rule. So this becomes x sine 1 over x minus f of 0, but f of 0 is 0. I'm going kind of fast now, is that all right? Over x minus 0, in other words, just x. So this limit turns out to be, the x's cancel, the limit as x goes to 0 of sine 1 over x. And that, we know, does not exist due to infinite oscillation. Right, so we're sort of doing a technical interpretation of the definition of the derivative, getting some weird shadow effect, but it's okay. So this function, therefore, our conclusion is f prime of 0 does not exist. Okay, should I do part 2? Do part 2? Part 2 is kind of similar. Part 2 says, but this g function is differentiable. What is g prime of 0? Well, again, using the definition of the derivative, it's the limit as x goes to 0 of g of x minus g of 0 over x minus 0. But that is, well, it's the limit as x goes to 0 of g of x is x squared sine 1 over x minus g of 0, which is 0, over x minus 0. Now the x's cancel, and this is the limit as x goes to 0 of x sine 1 over x. And this, via the squeeze theorem, is 0. So g prime of 0 is 0. It's a very technical problem. But if you can do that problem, then you definitely understand the definition of the derivative, continuity, and everything. Okay, I think we have time for like one more problem. That clock's fast. I think it's like 4:10. What should we do of those remaining ones? There were a couple I thought were like pretty important.